Hello, my name is Joseph Balderas, and today I'm going to be discussing deep reinforcement learning for crop production management. Crop management is essential for optimizing crop yield and minimizing the field's environmental impact, but it's challenging due to many complex stochastic processes that are involved, such as weather. Recently, researchers have turned to reinforcement learning, which is a machine learning paradigm which learns through trial and error. In particular, proximal policy optimization and DQ networks have shown promising results on the GMD SAP crop simulator. However, these methods have not been systematically evaluated under identical conditions. In this study, we evaluated PPO and DQN across three different RL tasks using consistent default parameters, identical reward functions, and the same environment settings. In reinforcement learning, the framework is as follows. You have a state space for the environment, an action space for the agent, a probability function, which gives probabilities transitioning to new states, and a reward function. And here in figure one, we see the RL framework in the context of crop production management, where the agent is the farmer and the environment is the crop field. So in reinforcement learning, the goal is for the agent to learn a policy or strategy which optimizes equation one, which is the expected value of discounted cumulative returns. In this study, we're going to focus on DQ network or DQN and proximal policy optimization or PPO. DQN works by training a neural network to give values to each action in the action space. And the idea is the agent wants to pick the actions that have the highest value. PPO works in a similar way. It learns a value function, but it simultaneously learns or it simultaneously estimates a policy gradient as well. And the innovation of PPO is it incorporates a specific type of clip function into its loss, which prevents new policies from deviating far from old policies. The RL environment that we're going to be focusing on is the GMD SAT environment, which is a crop simulator that simulates a maize experiment conducted in 1982. And the three learning modes are nitrogen fertilization, irrigation, and mix management, which is doing both of those tasks at the same time. Equations 4, 5, and 6 give the reward functions for each of these uh, for these modes. The box plots in our numerical experiment section show the test results of 1,000 test runs of the two RL trained policies against an expert policy and a null policy. So the null policy works by always applying zero fertilizer and zero irrigation, and the expert policy is a static policy that has been informed by expert farmers. So for the first box, we see the fertilization results. PPO does the best, and then it's the expert. And DQN surprisingly does worst here. For the irrigation box, that's the second one. We see PPO still does the best. The expert policy does second best. And then here, DQN does a better job at competing with PPO and the expert policy. And in the final box, we see that the expert does the best, but here DQN is in second place, uh, beating out PPO, which is somewhat surprising. On the right over here, we have 2D histograms showing the frequency of non-zero fertilization in the irrigation applications during testing for the fertilization problem and the irrigation problem. Here, darker areas correspond to higher frequencies. These 2D histograms allow us to visualize the policies that the PPO algorithm and the DQN algorithm are learning. Our results show that PPO outperformed DQN in individual tasks, while DQN outperformed PPO on the mixed task. One limitation of our study was the lack of parameters tuning during training, which likely impacted performance. Future work should focus on optimizing hyperparameters for both algorithms, as well as exploring alternative reward functions and crop management scenarios. Thank you.